Good evening, everyone. I welcome you all to the third day session in first principle, nanomaterial and quantum ticket and solar cell. In today's session, basically we go through the our DS-PAW software, which is based for first principle material simulation, which is based on uh, projected augmented wave and plane wave DFT. We also use Device Studio as a GUI to create the input file and create your model structure material file and go through the material simulation through the DS-PAW. Today agenda, basically we go through the introduction of DS-PAW, then the projected augmented wave method foundation, and after that we go through the core capabilities of DS-PAW, and after that we go through the key feature and function which is given in the DS-PAW software and their application area also, and also see the performance and future also for the DS-PAW. Basically, DS-PAW is a first principle simulation platform for a material research. It is core foundation on the plane wave DFT and the projected augmented wave for the pseudo potential. Here you can give the electronic configuration for the material also, and you can optimize your geometry, and the software enable researchers to understand basically material property and their quantum mechanical level also. Their main application domain are metal, insulator. You can introduce magnetic material, semiconductor, surface, and for the lithium-ion battery material also. This software tested on million of materials. You can see here, and you can see the here feature also like it integrate with the multiple exchange correlation function like LDA, GGA, hybrid function also, and it also include Havardio term, and where you can use the correction also like Wonderwall and DFT DF also. You can find the electronic structure properties like density of state. You can also find the projected density of state, electron localized charge also, partial charge you can find, Bader charge you can find, band unfolding you can do in the DS-PAW and the Warnier basis also. And you can relax your structure also through the multiple method like conjugate gradient, cosine Newton, NEV method, and AIMD through. And the fourth one is the magnetic property. You can introduce like collinear, non-collinear, and speed orbit coupling also. And you can also do the phonon, elastic property, dielectric properties, boron effective charge, and piezoelectric tensor through the small perturbation in the material. And you can find the optical property also. And you can do the solution model and fixed electrode potential in the DS-PAW software. If we talk about the theoretical foundation, it is based on plane wave, where we have done like basically for the pseudo potential and all electron method. It considers pseudo potential and for the accuracy also and the efficiency. You can see the advantage also, all electron accuracy, computational efficiency, and excellent transferability also. First, we have to give the partial wave, and after that, we assign the exchange collision function and define some parameter, and after that, it will create the input file. If you talk about the computation method of a DS-PAW, here you can see the exchange correlation function and correction also. It integrates with the LDA and GGA and hybrid function also. In LDA, GGA, you can see the GGA PB and LDA also, where you can assign the double zeta polarized and give the pseudo potential also. Hybrid function, where you can use the HH06 and HH03 for the electronic structure accuracy. You can introduce the correction also, like Havardio term for strongly correlated system. And you can introduce like DFT-D2, DFT-D3. Here you can see the functional type, 5 plus, hybrid options. And you can introduce the DFT Havardio term also and Wonderwall interaction also in the material. You can find the electronic structure analysis like band structure, projected band structure you can do. You can also do band unfolding in the DS-PAW software. And you can go through the density of state where you can find total density of state, projected density of state, splitting you can also do, and you can do TDOS also, total density of state. And you can do the charge analysis like Bader charge analysis for the electron density for atomic charge, partial charge density, where you can see the K point contribution, and you can go through the ELF also, like electron localization function, or identify the bonds and lone pairs. You can do the potential function also for a local potential, Hartree potential, work function, and electrostatic potential also. You can also do the geometry optimization in DS-PAW with multiple methods like conjugate gradient and cosine Newton, and flexible relaxation you can also do. Like for atomic position you can do, for lattice you can do, and for both. It means atomic position also and lattice you can do relaxation. You can do the NEB method for the transition states search, where you can use the NEB method for climbing image for the accurate barriers and diffusion in crystalline materials also. You can do the molecular dynamics, where you can use Born hyphen open hyphen MD and NBE, and you can do the post processing through the DS for post processing options. You can see some of the result which have generated through the DS-PAW software. Like you can see the phonon properties and molecular dynamics graph, like structure stability. Here you can see. Same way, you can introduce the magnetic property and spin effect also. Like you can introduce collinear, non-collinear spin orbit coupling also. And you can find the magnetic property like magnetic moment and the other parameters also, with the include of Havard term also. Here you can see for the linear response theory application, where you can find phonon properties, elasticity, dielectric properties using the perturbation theory, means small perturbation in the material. Like in phonon property, you can do the finite displacement, where you can find phonon band structure, phonon DOS, phonon density of state, basically. Thermal property you can find, vibrational frequency you can do. Apart from that, you can go through the elastic constant, where you can find bulk modulus, Young modulus, and Poisson ratio also. And through the dielectric properties, you can find Born effective charge, piezoelectric tensor also. And you can find the stability for the dynamical and mechanical wave also. And you can find elastic constant, thermodynamics, and for the phonon NEC for large range correction. Here you can see some of the graph attached, which is generated through the DS-PAW software, like for the charge analysis, you can see here. And you can see the thermodynamics property related to the uh, aluminum atom, oxygen atom, you can see here. And you can see the optical and transport properties also. You can find the optical property also, and you can find like refractive index, absorption, and reflectivity also. You can see some of the application here, where you can use for the 2D material, you can use for the battery material also, and you can introduce like magnetic and electronic property, where you can find magnetic movement and other parameter related to that, where you can introduce the spin orbit coupling also, and you can use the catalysis. Like you can use also the solvent model to analyze. Basically, DSPA give the efficiency to enable the researcher to explore material at atomic level and find the electronic structure through the molecular dynamics. And DSPA provide basically material for the design also. You can see the 30 plus tool present in the DSPA software, like AIMD, where you can use the molecular dynamics method. You can use the geometry optimization through multiple method like conjugate gradient, molecular dynamics, and VFGS also. And you can use the cloud also. If you want go for the cloud, you can use the cloud and use the number of code to simulate your material file also. Let's move to the device studio and simulate some material through the DS4 software and see the result. Let's create a new project here and give the name DS4 workshop. Earlier in last two sessions, basically we go through the device studio, where you can create your material file, create your devices also, create your crystal molecules, multiple things you can do in the device studio. At a single platform, you can do simulation through the rescue also, nano decay, BDF, MOMAP. You can see the multiple simulator option given here. You can also use VASP Quantum Espresso if you have. You can use device studio as a GUI to create the input file for the VASP and Quantum Espresso also. You can see the some quantum chemistry software also, NWCHEM, Gaussian also. At the earlier session, we basically go through the this toolbar option also. Again, I repeat, these at the top section, you can see the toolbar option, file to import your material file. You can see the new project, open project, save project. Through the new option, you can create a device also. You can create crystal. You can create your molecule also. And through the import option, you can import your material file. Let me show you. If I click on import local, here you can see Device Studio offer wide range of material database. If I go to the 3D material and go for layer material this time and click on boron nitride, and you can also see Device Studio support wide range of material format also like HZW, XYZ, CIF, postcard, SCF input. You can import JSON file also, molecule, and .s also, and PDB also. It means Device Studio offer wide range of material data format also. It means apart from that, HZW, you can import in the XYZ also, CIF also, and postcard also, like molecule and PDB. Let's import the boron nitrate here. Here you can see the boron nitrate structure, and at the left section you can see the property also for the boron nitrate, like total number of atom, total area of lattice, and the chemical formula also, and their coordinate also. If you want to see the property of this crystal also, go to the build option, and here you can see the standardized cell and symmetry option. If I click on symmetry, it will show the property related to the crystal also, like their name, crystal system, and their operator also. Here you can see. For a time being, let's simulate only two atom, because if we increase the number of atom, it will take some time. Go to the simulator. Here you can see the DS-PAW. In DS-PAW, you can do the structure optimization, electronic structure, NEB, AIMD. You can find the vibration like frequency, phonon, and other parameters. Let's do the electronic structure. First, let's go through the structure optimization. First, select our atom basically. Here you can see it will open the new window with name structure optimization. Here you can see relaxation. In relaxation, you can see the number of steps. You can also increase according to your material file. And you can assign the algorithm also, like conjugate gradient, cosine Newton, and molecular dynamics. Let's go with the default one, conjugate gradient. And you can see the relaxation convergence. It means you can give the energy tolerance level also and force tolerance also. Let's go with the default one this time. And you can see here degree of freedom. It means relax atom position only. You can relax all also and allow cell volume to change also. It totally depend on the user which type of relaxation they want, like relaxation of only atom and crystal also. According to that, user need to choose which one want, like relax all, relax volume to change, and relax atom position and cell shape also. I go with only relax atom position, and again go to the next step, which is solver setting. And here you can see the key point sampling, like gamma centered and pack also. Let's go with the gamma centered, and you can see the key point sampling 24, 24, and 24. You can see the sigma value for the Gaussian also. You can increase according to your material file, and you can see the cutoff factor and symmetry option. You can also do the for the false also, and you can include the convergence also for the energy tolerance and maximum steps. In the physical setting, here you can see you can choose the spin type like collinear, non-collinear. If I click on collinear, here you can see it gives the option for the set spin. You have to give the value here according to your material file. Same way for the non-collinear also. And in the non-collinear, you can also include spin orbit interaction also. Let's go for the non-stitch time. And here you can see you can introduce also Wonder Wall if you want. If I click on this, you can see DFT D2, DFT D3 also, and DFT D3 damping also. Same for the hybrid function. It also give the hybrid function like HSC06, HSC03, and B3LYP also. And you can also introduce Havadu term like DFT plus U, and it also give the option for DFT U plus and J option also. In nanodical and rescue, only it gives the option for the DFT plus U, but here you can go for the plus J also, and you can choose the functional type also like PAW, PB also. Here you can see multiple exchange correlation function given. You can choose also like regular for the element specific settings. And in advanced option, you can introduce the background charges also. You can correct the dipole correction, hybrid factor, and fixed potential. According to user data, you can choose like potential also, hybrid factor, and dipole correction also. For up to now, you can see the input file also by clicking on the input.in file. Here you can see the script for the relaxation like task, relax, system.structure, structure.h. It will generate a structure.h file. After that, you can see the functional type LDA, spin, none, symmetry, false, and you can see the sampling point and cutoff factor also. Click on OK and click on generate file. Here you can see in the project section, it will show the relax.input file. Open with, and you can see the script, same script. Right click, click on run. Here you can see, basically I connected to the cloud access so that it will show the number of nodes and number of tasks per node. I use 196 core here to simulate basically. Click on save and click on run. In the job manager, you can see relax.input. It not started yet. It will send to data the cloud and it will simulate there on the cloud access. I also show you by open the putty option, which is the open source terminal to connect through the SSH. Here you can see the path of the cloud where our the example is running. You can see the boron nitride here. Let's go inside this boron nitride file. Again, go inside the DS-PAW folder. You can see some of the input file or log file it will generate. And you can see the relax.h file, relax.input file, and structure.s file. It will show the relaxation steps also. It will take some time. For a time being, let me show the other feature also for the device studio. Import local 3D material. Let's import the layer material here, like WSE2. Delete by clicking on this, it will delete the atom. And by left click of the mouse, it will select all atom and click on center option. It will move your atom on the center. In the build tab, let's redefine. Click on preview to see the structure and click on build. To create the surface of the WSE2, there is option for the surface and slab option. Click on this. You have to give the mirror indices basically here to create the surface, and you have to choose the atom to define the most outer layer. Like if I go for the W and click on the slab option, you can, by defining the Miller indices and the choose atom to define the most outer layer, you can create the surface also and slab option also for the any molecule, any crystal. Now you can add any other atom like here for like NH3 and CO2 to create a device for the gas sensing devices also. You can create in this way. Here you can see the surface option for the WSC2 also. And here you can see the other option for the like measure the distance also between two atoms. You can see in this way you can do by clicking like shift. You can measure the distance also, like distance option given here. You can see by the right click, you can also see the display atoms also. You can also export their atom.xyz file. Here you can see their Cartesian coordinates. You can export directly from here. You can also assign the number of atoms also, like label, object type, atom, and number of atom. Click on apply. Here you can see number of atom also. It will show the number here like 9, 10, 12, 22, 21. This type of you can also do. Like to create a 4-probe devices. In earlier session, we go through the nanodical software where we only created the 2-terminal devices. Let's here create the four terminal device. And graphene redefined and go for a 12 cross 12 and create a graphene nano sheet. Click on build. By clicking on home icon, you can see the different view also like XY view, XZ view, YZ, YX, and ZX view. Click on XY. Here you can see the convert to crystal option. Click on this. You can also give here different type of crystal also, like you can give the cubic also, triclinic, hexagonal. According to user need, it also changes to the other hexagonal. You can assign that value here and it will show. Let's go for the user defined. Right. Go for the user defined and let's give the value here 0. Click on build. Here you can see it will show that outside the crystal structure. Left click of the mouse and there is option for the wrap. Basically, it will wrap your atom on the crystal like this. Click on home icon and click on XY view and let's select some atom here. Let's some delete atom here. Delete. Kindly save my number, sir. And since I am not able to send you my business card on a regular SMS, but I work for a company called Black Opal, and we are. Here you can see like plus. Now let's go to the convert to device option and click on bottom electrode, top electrode. Here you can see the value also, front, back, and click on preview. Here you can see it created the top and bottom electrode and front and back, top and bottom electrode. It will create like 4 probe devices. First probe, second, third, and fourth probe. 4 terminal devices basically. Here you can see. You can also change the length also. Here you can see 3 and give the value. Now you can see that it also changes the length also and click on build. Now you can see it created the 4 terminal devices. In this way, you can create also 6 terminal devices like at the top, at the bottom also, at this side, y-axis, on the y-axis. Here you can see the relax dot input in running condition. It will take some time. For time being, let's import another material. Like novelty material. And let's go for the 3D material, not 2D. Then semiconductor. Let's go for the gallium arsenide. and go to the simulator option, DS-PAW. Let's go for the this time electronic structure. Click on electronic structure. Here you can see first you have to create the SCF, self-consistent field calculation, to find basic parameters. Here we can see SCF. Let's include the potential also. Here you can see the potential. You can go for the local potential also and electrostatic potential. Let's go for the all this time. And in the solver setting, here you can see the value here, like K point sampling, gamma centered, sigma, similar type. You can see Gaussian also, cutoff factor, symmetry. You can see physical setting. You can go for the spin, non-spin, van der Waal. You can introduce in the material also, hybrid. Same way for the relaxation and advanced. Let's see the input file. Here you can see. Click on OK and click on generate file. In the project sector, you can see it created the input file, scf.input file. You can see the script also, like task scf. The structure taking from the structure.s file. Here you can see structure.as file, system.functional pbe, and the spin none, symmetry true, sampling g, and the cutoff factor and other value you can see here. Click on SCF input and click on run. After the relax.input file, it will run the scf.input file also. Again in the simulator tab, DS-PAW, electronic structure, you can see the density of state, band structure, potential, electron localized function to find like metallic bond, covalent bond, partial charge, Warnier. If I click on the density of state, here you can see the density of state parameters. You can give the energy range also, like -5 to 5. And you can give the resolution also, like 0.05. You can give the energy shift, like true or false. And like projected, you can project to density of state according to the orbital also. If I click on true, it will show the projected band according to the orbital also, and number of atom also. Like if you have different atom like boron and nitride, it will show for the boron also and nitride also on the orbital basis. Let's click on the generate file. It asking for the you want to use SCF input old one. Click on OK. And here you can see it generated a DOS.input file. Here you can see the script for the density of state also, like system.structure and system.spin type, K point sampling, cutoff factor, and here you can see it take initial charge from row. It will generate through the scf.input. After that, density of state will take data from the row file. And you can see the range also, -5 to 5, and energy shift and projected false here. Click on run. जैसे फाइनल स्टेज पे खत्म होने वाला हुआ था, तो बोला था कि कम से कम 3 हफ्ते लेके चलो, थर्ड वीक ऑफ अप्रैल फरवरी में आपको दिखाना शुरू करेंगे। तो मैंने ठीक है, क्या इसका कॉल आया तो वो देना भी पॉसिबल नहीं है। तो मैं तो ऐसे बता रहा हूँ कि राहुल ग्लोबल का फोन आया था, तो बोला नहीं ऐसा नहीं होगा, लेके बात होने से बात हुई, उन्होंने आपका नंबर दिया, उन्होंने इसलिए तो आपको मेरा नंबर दिया था कि हमारे पास 9 Again, go to the simulator option, DS-PAW. मतलब फायदा ही क्या है? Here you can see relax.input file completed, and it will generate some JSON file. Relax.json file. Click on show view. You can see the relax structure for boron nitride also, and you can see the simulation cell and particle types also. You can change according to your need. And you can see the raw file also for the relax.input file. Here you can see the total charge, tool D, average along Y, average along Z. You can change the color map also. And you click on the 1D to see the 1D graph also, like average XYZ plane. And you can change the length also, and their X minimum, Y minimum also, according to the control table. You can also export in image format and text format. And you can see the relax.dump file it will also generate. To see the proper structure for boron nitride. Now it's running the scf.input file for the gallium arsenide. Here you can see the SCF input file in running condition. Up for time being, let's generate for the PDOS also, DS-PAW, and electronic structure. Let's go for the band structure this time. Band structure. Here you can see the high K point path, like symmetric K point. I'm audible. Please confirm.
Yes, sir.
My screen is visible.
Yes, sir.
Okay, thank you. Here you can see the high K point path also, like symmetric K point. If you click on the path, it will open the belonging zone path also, where you can add and delete also and modify also the point also for the belonging zone path. And after that, you can click on preview, then apply. Here you can see the projected. You can also project your band structure also according to the orbital, and you can click on true for the PDOS. For time being, let's go for the pause and click on generate file. It asking for the using the SCF input like old one. Click on OK. And here you can see it generated the band.input file. Here you can see the script also. Like you can see the task, band structure, system.structure, and symmetry you can see here. K point sampling. and cutoff factor and sigma value. It will take some time. Here you can see SCF input file completed. Now it started the DOS.input file. And let's run the band.input file also. You can see the SCF input completed, DOS.input file in running condition. From the SCF.input file, it will generate potential and row file. Let's see the potential which is generated through the SCF input for the boron nitride. You can see the total electrostatic potential and total local potential. You can see the ISO value to change also. You can see the 2D graph. You change the plane display also like here. And 1D for total electrostatic potential, YZ plane and SZ plane. Same for the row file also, which is generated through the SCF.input file. Here you can see total charge, 2D and 1D. Here you can see DOS.input in running condition and band.input in queue condition. Let's create a script for the other parameters also, like simulator, DS-PAW. In electronic structure, there are other parameters also, like partial charge and Warnier function, ELF, and you can see the optical properties also. Click on optical. You can see the partial charge, ELF, and click on generate file. Here you can see partial charge.input file, ELF.input file, Warnier.input file. Open with, and you can see the script also for the partial charge. And you can see that it taking the data from the row file, which is generated through the SCF input. Let's run the partial charge and Warnier.input file also, and ELF also. I saw the previous example, which is I created for the silicon material. Let's open DS-PAW 0. Here you can see I basically take the silicon structure, and after that I relax the structure. It will generate latest structure.s file. Take this structure, like from file, import local option, and go to the project folder, like DS-PAW 0, go to the SI2, DS-PAW, and import this latest structure.s file, because it support .as also. Here you can see .as, and it will relax structure basically. Click on open, and here you can see the latest structure, which is optimized structure for silicon. After that, go to the simulator, DS-PAW, and find all these parameters. Here you can see DS-PAW electronic structure. It created a folder with name DS-PAW electronic structure. Click on this, and you can see the potential also for the silicon structure. Same for the row, 2D 1D structure, and you can see the band file, band structure for the silicon. You can see the band structure unfolding also for the silicon structure. If you go for the spin type, it also show the spin up and spin down option also. You can also export in text, image format also. And after that, here you can see the DOS also for silicon. Click on show view. Here you can see basically find the PDOS here basically. If you see here in the value control, here you can choose the silicon for the p orbital and the d, and go for the all. You can see the here all title here for silicon p d for single carbon, single silicon and second silicon atom. You can see the PDOS according to the orbital also. You can project through this element and orbital selection option. Here you can see the element and orbital selection option. You can also save in the image format also, and you can edit the value also like title, PDOS and other things like energy and density of state through the edit panel option. Here you can see the ELF, electron localized function. Click on this, show view. Here you can see the total ELF. 2D model is you can see here, and 1D also for different plane like YZ plane also and XZ plane you can see. Here you can see the optical also, optical properties, optical.json, show view. Here you can see absorption coefficient and photon energy graph. And you can see the dielectric function also, impedance dielectric function, absorption coefficient, and optical conductivity, refractive index, and you can find the reflectance also and energy loss. Here you can see. So these optical parameters. I also saw the projected band structure, which is created for the silicon. Go to the simulator, DS-PAW, analysis plot, and go to the project folder. And open the project folder like DS-PAW 0 in latest structure, in electronic structure. You can open the band.json file. Let's open other project where PDOS also present for the band structure also. और वो जो भाई का मांग रहे थे स्कॉर्पियो वाले अंकल क्या बोल रहे हाँ. Here you can see projected band structure also for the silicon crystal. You can choose the orbital also, like for all S, all P, and all D. You can select according to your need. Here you can see orbital for single silicon and all silicon, like D orbital, P, and click on all. You can see the data projected band structure also for the silicon crystal. Through the orbital projected option, you can choose. And you can also save in a image format and text format also. Here you can see. Let's create a new project for the NEB method. In the NEB method, basically we have to find a minimum path, minimum energy path. Let's import the structure here for minimum and the last structure. Import, import local. I created earlier. Here you can see the structure 0. Here you can see the structure. Let's import the second structure. And click on open. You can see the position of hydrogen at different coordinates. Here you can see. To find the minimum path energy, go to the simulator, DS-PAW, and there is option for the NEB, elastic band. Here you can choose the initial structure and final state. Just delete this one for time being. And go to the simulator, DS-PAW, NEB. Here you can see the initial state and choose the final state. Click on this and upload this one. You can select the number of image also and the ionic loop. Here you can see for the cosine Newton, conjugate gradient, and fire method, and other method also present here. You can see. Let's go for the cosine Newton. Solver setting, and you can choose the electronic loop if you want. And in physical setting, same way for the SCF input and other parameters also. In advance, you can include a solvation model also if you want. Here you can see solvation model. For up to now, you can see the input file here by clicking on this input file and click on OK and click on generate file. Here you can see it generated the multiple folder with name DS-PAW NEB. And at the last, you can see the NEB.input file. In all structure, you can see the structure, different structure also. And here you can see NEB.input file. Open with. You can see the script here. And let's run the NEB.input file. And click on run. It will take some time to compute. Let me show the documentation also for the DS-PAW. If you type hjw.ai, it will open the website. Here you can see the product also, like for modeling and visualization, you can see at the top, Device Studio as a GUI, BDF, DS-PAW. Click on DS-PAW. You can see the main function also there. Exchange collision function, electronic structure, structure evolution, magnetic property, linear response theory, and optical properties. Click on website. It will open the manual of DS-PAW. It will take some time. It is so. Here you can see. You can find all types of parameters like background charge calculation, optical property calculation, frequency calculation, elastic constant calculation, transition on state calculation, phonon spectrum, molecular dynamic simulation, external electric field calculation, ferroelectric calculation. You can calculate in the DS-PAW, battle charge analysis, band unfolding, dielectric constant calculation, solid state NEB calculation. You can see here, solvation energy calculation, Warnier interpolated band calculation. You can see here. If I go below section of this website, this manual, you can see the band structure calculation. You can see the band structure also, projected band structure. You can see the DOS also, PDOS. You can see the potential also. Here you can see the potential. You can find the ELF also and partial charge. You can find the band structure through the HSCD06, which means hybrid function you can use to find the band structure, accurate band structure. Here you can see the graph also. You can find optical property, which also I show you in the silicon crystal. You can see the NEB now, and you can find this type of graph also, the energy and force for the obtained during the relaxation process. This type of graph you can find. Number of ionic steps. And there is option for the post processing also. Using DS-PAW Python, you can use the post processing tool also for the extracting the data also and plotting different way of graph also. Like you can see, using the Python script, you can convert also input file in the other format also. Like how to do the volumetric data processing and plot this type of graph using the post processing option through the DS-PAW. Like 3D planar structure. and you can find the headband for the any crystal, any material file also, like this. You can plot also according to the orbital also in the different graph, like this one, d orbital, and for the other atom, you can sulfur, you can use the plot for the s orbital also. In this way, you can do the post processing through the DS-PAW file, like this one, for px orbital, py, and pz. You can do all the post processing for the band structure, optical, and other things also. Let's move to the NEB example. It will take some time. Let me show the simulated result. Same NEB method. Here you can see it's simulated basically here. Let me show the result here first. Log file and JSON file. You can see the reaction coordinate also for the NEB. And you can see the control level where you can give the x minimum, x maximum also. And convergence you can see here for the NEB. You can choose the structure index. And you can see the trajectory also. Like you can animate. You can see the structure, how to minimum and latest structure. We also go for the FP203. Wait, let me show. For spin and total charge also. You can see here. And 2D and 1D plot here. Basically, in this example, we simulated through the spin orbital interaction also, where we created through the spin orbit interaction, and it will generate the band structure according to that. It's not simulated at. Or up to now, if anyone have doubt, please ask. Related to the material and DS-PAW software. If anyone have query, please ask. You can also write in the chat box also if you want. If someone want trial license for the software, they contact us on our mail and number also. Anyone have query, please ask. You can see the structure, gross structure also for the boron nitride here. You can see. You can give the X minimum, and you can see the graph also. You can change the color also. Here you can see the DOS also. Now you can see the band dot input file in running condition. You can see the log file also to see the data related to that. Like you can see the information, total number of process. Basically, we're using here one process, and the file name and the pseudo potential for the gallium. Weight form loaded. You can use the pseudo potential here using the DS-PAW pseudo potential database, and you can also use the WASP pseudo potential in the DS-PAW software. There is three format where you can upload the DS-PAW pseudo potential also, and you can upload the WASP pseudo potential also if you want. It support the WASP pseudo potential also. Here you can see the process also like K point, reduce K point, and after that it started the SCF parameter. You can see the task SCF, and it loaded the structure and solved the some iteration steps. You can see here. In the log file, you can see the process also and the total time taken, all these things. And the error, so if something error happen, it will also show in the log file also with the error code. You can see now it's doing for the band structure here, number of iteration steps. Let's go for the AIMD also to see that other parameters also. Here you can do DS-PAW, AIMD, molecular dynamics, into molecular dynamics. You can choose the thermo properties also through the NBME multiple method, NBT, NPT, NPH, SA also. And you can use the solver setting. In AIMD, you can use the simulation parameters, temperature and pressure you can initialize, like initial temperature you can give and final temperature you can give. Solver setting, physical settings, advanced options, and after that click on generate file. It will create the DS-PAW AIMD. Here you can see AIMD.input file. Open with. Here you can see the script also. Same way you can generate for the phonon also, like frequency. Go to the DS-PAW. There is option for the vibration, where you can find phonon, frequency, elastic constant, and epsilon also. If I go for the phonon, you can see the method here, finite displacement and linear response. You can choose according to your need. And in frequency, you can see the other parameters also. Sorry, phonon. And you can see the frequency also, displacement mode, displacement range also, elastic constant, like for the supercells size, density of state, band structure for the unfolding band structure, and epsilon also you can see here. And click on generate file. Here you can see it created a multiple folder like phonon, frequency, epsilon, and electric constant, elastic, you can see here. It will take some time to compute. For up to now, let me show you the post-processing option also. Here you can see there's some script related to that to plot some graph like for total electrostatic potential. If I run this,
जैसे निर्भय है ना, निर्भय ने पीछे से कितनी विजिट करानी है, मतलब कि मुझे जैसे निर्भय का मुझे याद है कि निर्भय विजिट कराता है तो मैं
some graph also.
निर्भय ने कम से कम 4 विजिट कराएंगे, तो बीच में किसी भी डेट की डाल दे, निर्भय ने 2 सेल की 2 रेंटल की, मतलब ऐसे डाल दे।
Here you can see the result also for the DS-PAW, which is going to the post processing. Through the post processing, we can find this type of graph also for the total electrostatic potential versus grid index also. For up to now, if anyone have doubt, please ask. If someone want the license also, please contact us. I write the mail also in the chat box and number also. You can directly contact us regarding the license and demo part also for the other software also. Anyone have doubt, please ask. In tomorrow's session, basically we go through the solar cell module where we find 4 module and find like layer module, objection module, and EM module to find other parameters for the solar cell, perovskite, tandem solar cell, and all these type of parameters using the set software, which is where you can find other parameters like IV curve and other parameters related to solar cell.
वो मैंने कर लिया, तो भाई मैंने डाल रखा हूँ 99 एकड़ पे, वो के रेंटल नीचे।
For up to now, if anyone have doubt, please ask. You can write in the chat box also. Now let's end the session here. In tomorrow's session, please come for the solar cell also, where we will learn about the solar cell, perovskite, tandem solar cell. Yes, you can use the gas sensor devices also in the device studio. You can create gas sensor type of devices using the nanodical software, which taught earlier in last session. Where you can easily simulate the gas sensor devices and find the property related to that, like charge transfer and other parameters also, using the density function theory and non-equivalent gain function in nanodical software.
अच्छा, वो ऑफिस फोन पे लोग हैं, ये पता है।
Please contact us for the demo and license version. I sent earlier the message. Yes, you can mail us on this mail, and you can contact us at this number also. Please contact us on the support@impulsetechnology.in for the license. Yes, you can do the doping also. I'll show you also the doping also. If I import any material, let's go for the, like, consider the WSU2. You can do the doping by replacing any atom also, like this, replace with other atom also. Like, go for the phosphorus. You can see the structure. Here you can see the phosphorus also. And you can directly simulate your material through the nanodecal and rescue also. And there is another option in nanodecal. There is option for the virtual crystal approximation, which is used for the doping also. Here you can see doping type you can choose. P type, N type doping you can choose, and you can give the value here also. Apart from that, you can use the mixer atom also here. You can see element phosphorus composition. You can see, click on this, and you can choose any element like oxygen, and you can give the value here. Like, let's consider 0.8 for here and 0.2 for the oxygen, and you can generate file. It will generate a mat file which can use for the doping also.
Six DDR5 LPDDR. We can't able to get the full data set because it's licensed for the particular customers only. So that
Monica
is
ma'am, you
also
can
caused
contact
the
us
issue.
after the session
So for
for
AI
the
workloads
dump
with
file.
DRAM or any other memory architecture, we need to make some circuits, which
Abhishek
is
sir,
what
please mute
the
yourself.
upcoming shift.
So try to get the same, like just like the SRAM cell, no, try
If
to make the
anyone have
DRAM
doubt,
cell.
please ask. You can do the doping in that
Because
way.
time
You can
wise, you know
generate
well how much
through the
VGA,
by
how
replacing
many
atom,
GB are.
and there is another method through the
But
virtual crystal approximation.
this is a very good opportunity, but except you, no one else is there. Sir.
Thank you everyone for joining the session. Please join the tomorrow session for the solar cell also.
Everyone easily now the placements also like
Ma'am,
switching
please
the
contact
domains
us for the
very
license
much
version for the device studio
of
and
course
other
I
license
will definitely
for
get
other
into
simulation
it. But let's
on the
see
support at
whatever
Impulse Technology.